Good afternoon, everybody. Let's get started. So for announcements, there is no lab this Friday. The first lab will be Friday, September 6th. So during that lab, you're going to join a lab partner. So you can decide on if you want to choose a lab partner in lab or before lab, whichever. You can do that at the beginning of lab if you want. We will be distributing the lab component kits. And then I will have you start the test bed structure build. So you'll get an explanation of what the structure is, and it has to house the electronic components for the semester. And I'll show you some examples. And so we'll talk about that. And then you'll have a week to finish that up and then start doing some real electronics work. Actually, you will work with the DC motor and measure the DC current and the DC voltage and the power required by the motor to turn full speed. So we know how much power your motor controller has to control. So that will happen at the first lab Friday, September 6th. Also see the Canvas page for assignments. So there's a homework assignment coming up. That's homework 1. That due date and due time is listed there. So let's jump right into the lecture material. We talked about an introduction to the course last time. I gave you all the logistics for the course. And so what I wanted to start today is 2 or 3 lectures on circuit theory and analysis review. So we'll go through this fairly quickly. I want to point out some practical applications and implications of some of the circuit theory, circuit analysis that I think you'll find interesting, even if you've seen this material before. I'll show you some new material here. So we're going to review these topics and talk about basic circuit theory in the context of analysis and design of practical circuits. And I'm going to relate these fundamental concepts to some what I think are useful applications. So if we look at these topics we're going to review, we're going to talk about circuit variables, so voltage, current, power, resistance and Ohm's law, capacitors and inductors, Kirchhoff's laws and voltage and current division, and the Thevenin equivalent circuit. So these are all the things we covered in the intro class if you took my class there. But what I want to add to this, in addition to a quick review, are some practical examples and impact on designing a circuit. So for example, during the intro class or during your intro class, you probably talked about node voltages and node voltage analysis in the context of we have a circuit, we have resistors, we have some maybe current sources. And so solve for all of the node voltages given a ground or a reference node. And so what I want to show you is, well, we don't always call them node voltages when voltages are called out at nodes on a schematic. So I want to show you that and then talk about node voltages in physical circuits, like a microcontroller board. And we'll talk about power and energy. And I'll show some examples of, for example, the cost of operating devices based on the cost of energy and portable device life when you're running off of battery. Okay, for resistance in Ohm's law, right, V equals IR, but I want to talk about resistivity of wire materials and voltage measurement and power loss for non-ideal conductors, right? So conductors, we assume when they're on a schematic in the classroom that they are ideal conductors, but there are situations where you have to take into consideration the resistance of conductors, which means they're non-ideal. So we're going to talk about the impact of wire gauge and selecting wire gauge and selecting operating voltage for power transmission. We're going to do an example where you have a solar panel, multiple solar panels, and so what if you hook them all in parallel, all in series, you have a certain gauge wire, you change that gauge wire, how much power is lost, what's the power efficiency, what's the cost of going to a more efficient setup, or the cost savings. We're going to talk about, well, capacitors, but I want to point out, because you'll need these in your project, decoupling capacitors for DC power supplies and how those capacitors remove noise from, well, sensor signals and also digital signaling and power supplies, power supply voltages that should be clean. So we'll talk about that. We'll talk about inductors. I want to show you an example of electrical filtering for removing undesired signals and noise, and also the size and weight impact of using inductors. And so your mechanical engineers, you care about size and weight, and well, after this class, power too. And we'll talk about Kirchhoff's laws, really quick review, but I want to show you an example that I actually ran into for a circuit design where there are connector engagement and pin engagement considerations and sequencing of power when you power up a circuit to avoid damage levels. This will just be one example where I think you'll see it's relevant. And then we'll talk about Thevenin equivalent circuits in the context of what if you have a receiving antenna, right? We're going to talk about a little bit of RF in this class, radio frequency in this class, wireless. And if you have a signal from a receiving antenna and you're trying to sample that signal with an analog to digital converter, what voltages do you expect? How do you know that you're going to span the full range, or at least enough of the range of the ADC, of the analog to digital converter? So on the left, all of the things we covered, or you might have covered in your class, for intro to circuits. On the right, some examples where I want to point out that these topics really matter. All right. And if you have any questions or want to talk about anything during class, just shout out a question or shoot me a chat. So if you would, grab your clicker apps, and I'd like to do a survey just to make sure I understand where we're all starting, or most of us are starting in this course. So let's see. So this is a survey. What kind of circuits experience do you have? And I'll build this out to 3 choices, A, B, and C. But do you have pretty much minimal circuits training, like you took a physics class only, or that's your primary source of circuits knowledge? You haven't analyzed using Kirchhoff's laws, Ohm's laws. You haven't done any voltage division or current division problems, right? Or have you taken mostly classes and taken a lab, right, for some practical design? Did you do some training in circuits, maybe outside of class and beyond physics? And are you familiar with the basic circuit analysis, Ohm's law, Kirchhoff's laws, to calculate voltage, current, and power? Have you calculated voltage and current for first order circuits using differential equations? Are you familiar with phasors and impedance? Calculated a Thevenin equivalent circuit? Or are you really experienced with circuit analysis and design of circuits, like really comfortable with RLC circuits, calculating frequency responses, maybe of filters, choosing wire gauge based on resistivity, operating voltage, calculating power efficiency, and applying capacitors and inductors to filter, let's say, power supply circuits for decoupling, and maybe have done impedance matching to resonate out reactance? So take a few seconds, answer that. That will help me focus the material and also extend out kind of to the tails of the curve to give everybody something out of the course. All right, good, thank you. Looks like most people fall into B, which is what I expect. You've probably taken a circuits class, worked in a lab in school, and so that's good. Okay. Okay, so let's talk about circuit variables. You remember this from intro to circuits: voltage, current, power, and energy. So current is the flow of charge. Current describes the rate of positive charge flow. We in electrical engineering like to talk about positive charge flow. Physicists like to talk about negative charge flow, electron flow. We just choose to talk about positive charge flow. So the unit of positive charge flow is coulombs per second. So coulombs, that's a unit of charge. Seconds, that's time. So this is some kind of quantity of charge per second. It's a rate, it's a flow. And current is always described using a quantity and a reference direction. So current might be 2 amps, but it flows in a certain direction, right? In this case, I have a wire, and somehow I have this wire connected to something on either end, and I have positive charge flow, and this is showing the the direction of positive charge flow. And so in this case, Ix, that variable that represents the quantity of current, also has to have a reference direction, which is the arrow. So if I have 2 coulombs per second, 2 amps flowing, then Ix would be 2. If charge were flowing the other way, positive charge were flowing the opposite direction, I just reverse all the red arrows, but I leave the blue arrow in the same direction, I would have a negative quantity, negative 2 amps. It's just fine to have a measurement of negative current, right? So, and when you talk about current, use words like through, right? Use when describing current. So current usually flows through a wire, a conductor, a component. So voltage is a measure of energy delivered per unit charge, the formal definition. Okay, so voltage is the potential to do work. And it describes if you were to flow charge, let's say through this battery somehow, how much energy would be transferred per unit charge or per coulomb. So a volt is a joule per coulomb. Joule is energy, coulomb, that's charge. So this is energy per charge, right? So it describes how much energy would be transferred if charge flowed. And voltage is always described between 2 points and has polarity. And voltage can be positive or negative, right? So I have this 9-volt battery. I have 9 volts with this polarity, positive on the right, negative on the left. It means on the right, that terminal is 9 joules per coulomb, 9 volts higher in potential than on the left. So voltage always has to be described between 2 points. It's like altitude, right? I like to use the example of altitude. My hand is at 5,300 roughly feet above mean sea level right now. Okay, so the 2 points are my hand and mean sea level, or my hand is 3 feet above desk level, right? So you always have to have 2 points to measure height or altitude. You always have to have 2 points to measure voltage. Okay, so you use words like across or between when describing voltage. So voltage, the voltage across this battery is 9 volts. So the voltage between these 2 terminals is 9 volts. You don't ever use like through. You wouldn't have a voltage through something. It's not a flow. Current is a flow, right? But voltage is it's a difference between 2 points of the potential to do work. Okay, power. Power is a rate of energy transferred. Okay, it's the rate of energy transformed to or from other forms of energy. So, we're not creating energy, destroying energy, but when you take the energy from a battery and you heat a coil, so you're transforming that chemical energy stored in a battery to energy that shows up as heat and light. So power is that rate of energy transfer in joules per second, joules, energy, seconds, time. So that's a watt. And power, a lot of people don't like this, but we do it. Power can be a positive or a negative value. Okay. If you're using what's called the passive reference configuration, you can click on the review video on power on Canvas if you want to review that. But if you use the reference direction of current pointing into the positive sign of a voltage defined, then multiply those 2 numbers together, voltage times current. If P is greater than 0, that circuit element is absorbing. If P is less than 0, that circuit element is supplying. So the lit up coil here would be power greater than 0. This battery, if it's supplying energy, supplying power, would have power calculated less than 0. When we're talking about power for a circuit, we usually use words like absorbed or supplied or delivered, dissipated or consumed, like words like that. Okay. And so I talked about power before energy, so I should really mention energy first, but energy describes the amount of work done. And it's often described in joules in physics, right? Often in practical applications, especially AC power systems, like power delivered to your house, we talk in units of kilowatt hours. Okay, so a joule is a unit of energy. A kilowatt hour is a unit of energy, right? Kilowatts, that's an amount of power, which is joules per time. So this is joules per time times time. You get joules, right? So this is a unit of energy that's pretty common, especially in AC power systems. And we use, again, words like absorbed, supplied, delivered, dissipated, consumed. The same thing, same kind of words we use for power, we use for energy. Right? Power is just the rate of energy transferred. Okay, so if any of these, if you're comfortable, great. If not, please see the videos that I've posted, and you can index into, you can click on to the points in time in those videos to review current, voltage, power, and you'll see that on Canvas. All right. And again, shout out any questions or put them in the chat. So let's talk about node voltages. We talked about node voltage analysis in the course, so I had to define node voltages in the intro course. And node voltages require a ground node, and we call that a reference node. So a node voltage is a voltage defined still between 2 points. You have to have 2 points to define a voltage, but it's defined between a particular node and another node, a second node, which is the reference node. We often call that ground. So you're going to be using a microcontroller board in lab, and it's this microcontroller board. It's a pretty neat little board. This looks like if you've worked with an Arduino in some former class, earlier class, this probably looks a lot like the board you used. One of the common boards is the Arduino Uno. This is actually the Arduino Uno Wi-Fi, which has a few cool features on it. One additional feature beyond the regular Uno is that it has a Wi-Fi module here. This module has a whole Wi-Fi transceiver in it, and then this little slot right here with this metal, this is the antenna. And so that's the built-in antenna to this whole board. So it has that. We'll work with that. This is an inertial measurement unit, IMU. It's a 6 degree of freedom, which means it has X, Y, and Z acceleration and X, Y, and Z axes gyroscopes built in. So this is the board I wanted to point out we'll be using. You'll see you have access to the terminals here. This is called a header. These are holes into which you can stick breadboard wires and then solder to those wires or run those to your breadboard to have access to the signals of the microcontroller. Here's the microcontroller here. And also you have access to, we'll talk about this, analog to digital converters and digital ports. But you also have voltages here. Like you'll see called out right here, 3.3 volts and 5 volts, right? Here's the header hole that you would insert a wire to access 3.3 volts, and this is 5 volts here. But what those are node voltages. We often don't say that. We don't call it out explicitly, right? But for example, 5 volts, right? That 5 volt pin right there, or socket. That 5 volts is still between 2 points. It's between this header, socket, and ground. So there's a common ground for this whole board, one single common ground. And whenever you see a node voltage or a voltage written next to a single conductor, like this header pin, header socket, that means it's with respect to ground. So if you measured between wires that were inserted between these two holes here, you would see 5 volts. Okay, the 3.3 volt, that's also a voltage between that socket and ground, right? So all of the node voltages are reference to ground. So when you see a board, when you see a circuit, and voltages are called out for a single point. Remember, voltages are always between 2 points. There's always going to be a ground if you have a single point with a voltage called out. Okay, so we when we define a voltage at a single point, we're defining a node voltage implicitly, and it has an implied polarity. And the positive always goes at wherever the node voltage is written, like 3.3 volts. That's where the positive side is. Negative always goes at ground. It doesn't mean you can't measure voltages elsewhere in the circuit by moving the negative terminal of your voltmeter. But if you're dealing with a node voltage, the negative is always the ground or the reference node. And in practice, you won't often hear electrical engineers after they get out of school talk about node voltages unless they need to clarify something. But they'll talk about voltage on a wire or at a wire, right? But that implies that there's some ground node somewhere. So they're talking about a node voltage. Okay, so if a voltage value is defined at a single point, that's a node voltage. Looking at a schematic, here's the schematic of your project. Okay, so you're going to be building this throughout the semester. Here's the microcontroller board just drawn as a box. This is that Arduino Uno Wi-Fi board. Okay, and then there are, well, other circuits around this. All right, so the microcontrollers, the brains. We have batteries and a DC to DC converter to convert the battery voltage to the voltage that the motor needs, and then a motor controller circuit using a MOSFET here, an infrared sensor that will sense blade crossings so that you can calculate RPM with software, a few sensor circuits using voltage dividers, okay, and a temperature sensor over here, and then a USB connection. So you'll notice on here, relating this to node voltages, there are several voltages called out, VBAT, right, VSM, and most of the voltages defined here are node voltages. VTemp, VSMA, VCCA. There's no polarity drawn. There's no positive, no negative actually called out. I have plus 5 volts here. That's done with power supplies because sometimes you have a negative 5 volts or a negative 3 volts. So this is just clarifying. That's a positive 5 volt supply, but that's not really a polarity marking where there's a negative somewhere else. Right? The implied negative of this plus 5 volts or this IR det, the implied negative is at all the ground symbols. Now you see all these ground symbols, right? I have a ton of them here. They are all assumed to be one node. They're all connected to the same piece of metal, right? Somehow you go through wires or breadboard connections or a circuit board, and they're all connected to the same node. So even though they're all drawn separately here, that's just for convenience. So I don't have to connect a wire between all these and make the schematic really cluttered. So all of those grounds, it's important when you're building your circuit to connect all those together. It's also important when you want to measure a node voltage that you connect, let's say you're using an oscilloscope, the negative lead of the oscilloscope should connect to the ground of the circuit. And then you can probe through and see V control or VSM or VBAT. Okay, so all these node voltages are referenced to ground. There's one voltage here that is not referenced to ground, and that's V motor. So the motor is connected to between two nodes, between 2 points in the circuit, and neither of those points is ground, right? This does not connect to ground directly through the MOSFET, which controls the motor. It's connected to ground, but directly the terminals of this motor, neither is connected to ground. And so we're going to want to either measure or determine the voltage across the motor. And so we have to put an explicit polarity there, plus minus V motor. So when you don't have a node voltage, you have to write those polarities. Okay, so V motor is not a node voltage. I think everything else here, every other voltage indicated is a node voltage. And I'll probably never say node voltage again as we're talking about the circuit. I'll just say the voltage between R5 and R6. Right? What's the voltage at the wire between R5 and R6? That's implied. It'll be a node voltage. All right. Any questions on this? Anything of interest here that you'd want to talk about? We'll get into this very deeply in lab, how all this works. Okay. All right. How about a quick review of Ohm's law and resistance? Right? You know Ohm's law. Resistor is a device that behaves according to Ohm's law, and there actually are a lot of devices that behave according to Ohm's law that are not resistors. You know, a speaker, an antenna, like an RF antenna, um, certain circuits like the input to an audio amplifier or any kind of amplifier. Often they behave like a resistor because they follow Ohm's law. This is Ohm's law. Ohm's law simply says that voltage. So for a device that behaves like a resistor, voltage is proportional to current, and the proportionality constant is R, the resistance, measured in ohms, right? An ohm is a volt per amp. That's what it is, but we call it ohms. So if you have a voltage defined across a resistor or a device that behaves like a resistor, if you have a voltage defined with the positive on the left and the current is drawn with this reference direction going into the positive sign, then V equals IR. Okay. And resistors look like this. These are the style of resistors, stick lead resistors, or let's see, leaded resistors that you plug into circuit boards that have holes in them. These are surface mount resistors that get soldered to the surface, pads that don't have holes through them. So you'll see these on the circuits that we use and build in lab. And resistors dissipate power. All resistors dissipate power. Right? And sometimes you actually use the resistor to dissipate power. One example is if you need you know, a load for a transmitter, right? You don't want to transmit energy. You want to actually have that energy just be absorbed. You can use a resistor for that. Sometimes you need to just get rid of energy from a solar array or a generator, and you can dissipate that power in a resistor. They get hot. That's what they do. If they get really hot, they light up. That's usually a bad sign. You can use resistors to set the current through diodes. So if you're trying to build a circuit that has an LED in it, you limit the current through the LED using a resistor, and you can set the gain of op amps, right? We did that in my circuits class. You designed a non-inverting amplifier or an inverting amplifier, and the way you set the gain of that circuit was using resistors. So in that case, the point wasn't to dissipate power. The point was the relationship between voltage and current, and when we did the calculations, that set the gain of the circuit. So resistors are useful there. Resistors have power ratings, and if you exceed the power rating of a resistor, you can damage that resistor. It gets hot, it burns out, it either fails open, or its resistance changes because you burned away some of the material. Examples are these chip resistors, surface mount resistors. Here's a 1/16 watt resistor. These are quarter watt resistors. You look at the data sheet, you figure out the rating, and you want to keep the power dissipated on average below those ratings. And sometimes in products, you derate the resistors by 50% or according to some curve that your reliability engineer gives you. This is a 10 watt power resistor. That's a pretty big resistor. This is probably, I don't know, an inch or two long. And here's a really big, a really well heat sunk power resistor. This is a 50 watt. Oh, this says 50 watts. This says 10. I got that wrong. So this is a 50 watt resistor, 10 ohms. And so you can heat sink this to a case or a heat sink fins. There are standard values of resistors, and resistors typically depending upon their tolerance, are given in these standard values. So 5% resistors, these are what you have in lab. This means uh, if you have a 5% resistor, you can only find these values, right? You have 10 ohms, 11 ohms, 12 ohms, 13 ohms, or multiply these by 10, 100 ohms, 110 ohms, 120 ohms, 130 ohms, multiply by 100, 1000 ohms, 1100 ohms, 1200 ohms, right? So it goes all the way up from ohms, single digit ohms, all the way up to mega ohms, larger, but only in these values times 10 to the n. And if you need exactly let's see, a 2.1 k ohm resistor, well, you can put two resistors in series to get that. So you can see the E series for an explanation of there's a way these are calculated, but these are the standard values. But this 5% value, that's a tolerance. So the tolerance describes the deviation from its nominal value at 25C. So if you have a resistor that you pull out of a box, oftentimes that tolerance is, well, if you have a 1,000 ohm resistor, it could go up 5% by 50 ohms or down 5% by 50 ohms. And that's what you would see. And then there's also temperature characteristics of resistors. And common tolerances are 1% and 5%. And you can get precision resistors. Okay. So if you need for your op-amp circuit a very precise gain that doesn't change over temperature and doesn't change from resistor to resistor as you build these, you can get resistances that are 0.1% tolerance. Right. So you can buy resistors like that. And they're more expensive. So, why not build every one of your circuits with 0.1% resistors, because they will work like you expect. Well, they're more expensive. So if you look at the price of this resistor, 0.1%, it's 21 cents each. And if you look at the price of a 5% resistor, it's 1 cent each. So it's 20 times the cost to get that tolerance. So if you're building many of these, you might want to consider cost. All right. So that's Ohm's law. You'll be using these resistors in lab just as a refresher. Resistors have color codes. So here's the color code chart. You can even print this slide out and take it to, with you and stick it on your bench in lab if you want. So an example is this brown, black, red, gold banded resistor, right? Brown, black, red. Brown is 1, black is 0, red is 2. Okay, so first band, that's the first number. Second band, that's the second number. The multiplier is times 10 to the power of. Right, so this is a 1,000 ohm or 1 k ohm resistor. And the gold band means it has a tolerance of 5%. So that's what you'll have in your kit. And oftentimes, I don't think I've ever seen a resistor out of the box deviate by 5%. So, I wouldn't count on it. You don't do your reliability calculations with my anecdotal experience here, but usually resistors are pretty close to their given value. Okay, so let's look at power calculations. Let's talk about calculating power for resistive loads. Okay, so if you have a resistor, and again, this resistor could be any device, any component that behaves according to Ohm's law. So this could be an antenna. This could be an antenna that looks like a 50 ohm resistor. And you would do the same kind of calculation as long as the device looks like a resistor, V equals IR. Okay, so I have a time varying voltage and a time varying current defined here. And whenever you calculate power for Ohm's law, have the reference direction for current pointed into the positive sign of the reference polarity for voltage. Okay, and if you need to if you need to flip those to make that happen, then I would write negative in front of the variable that I flipped. All right, if you want to see example calculations, see the review videos for power calculations. Okay, so for DC voltages and currents, like a battery or a DC power supply, V of t is a constant, I of t is a constant. So we could just call those V and I. Power is I times V. And for a resistive load, V equals IR, that's Ohm's law, and power is equal I squared R, equal to I squared R. I is equal to V over R, right? So power is V squared over R. So that's where these power calculations come from for resistances. Okay, so this is DC. This is a DC example here. For AC voltages and currents, and as an example of that, right, if you had an antenna that acts like a 50 ohm resistor and you're trying to transmit signals, that's going to be an AC voltage, AC current. We'd express that voltage and current as a sinusoid, as sinusoids. So we have some peak value of voltage, a frequency, and a phase. Okay, so when you have, when you apply a voltage that is AC across a resistor, the current is that voltage divided by the resistance, right? And resistance is a real value. It's not imaginary. And so you get a, if we were using phasors, right? Flashback to phasors. But voltage and current then would be in phase, right? The zero crossings of voltage and current would happen at the same point for a resistor because they're just proportional by the resistance. We use RMS values, root mean square values, to calculate average power. And root mean square is calculated like this, right? Here is the root of the mean, right? 1 over the period of the waveform times an integral of the square of the waveform over that period. Right, so here's how you calculate RMS voltage. Here's how you calculate RMS current. And if you have sinusoidal waveforms, it's really easy. The RMS value of voltage is the peak value of voltage divided by root 2. Right? Similarly for current. So resistive loads, P average is equal to V squared over R, but you're using the RMS value of voltage. P average is I squared R, but you're using the RMS value. And you can use I times V RMS values. Okay, but again, these are resistive loads. That means voltage and current are in phase. Right. So if you have a an antenna, I like to use antennas as examples because they don't look like resistors, right? They're not a component, but they behave like resistors because if you measured voltage, measured current, they would be proportional, and if they're sinusoids, they would be in phase for a well-designed antenna. And so you would see, if you want to calculate the power radiated from an antenna that's highly efficient, right? A highly efficient antenna, you could use this. You could say, oh, I know the peak value of voltage across the terminals of the antenna. I know it's a 50 ohm antenna. You can calculate the power radiated. So there's a lot of use here in just Ohm's law and just power calculations for components beyond just resistors. So this power calculation, again, I warn it's for resistive loads because if you have inductive or capacitive loads, the voltage and current are not in phase. Okay, and so you can't use these equations for calculations for inductive or capacitive loads unless you apply a power factor. We're not going to get into that, but that's if you're dealing with AC power, you learn about power factor for capacitive and inductive loads. All right, any questions on what we have talked about so far? Okay, let's work a clicker problem then. Let's talk about energy delivered to a load that we're going to approximate as a resistor. So let's suppose you're performing research and you have this experimental setup and the equipment requires 120 volts AC. Okay, and you don't have an AC outlet available. You have a 12-volt battery, you have a power inverter. We'll talk about these. And so this converts 12 volts to 120 volts. And you're going to model this equipment as a 100 ohm resistive load. And you need to run this equipment for 24 hours. Okay, so the equipment looks like a 100 ohm resistor. That's a stretch, but it's an example. You have 120 volts AC, and that AC value is an RMS value. So home power, right? Residential power. If you were to measure the voltage between the two terminals, don't do that. It's dangerous. I have to say that. You would measure 120 volts RMS. But if you wanted to know the peak value, measuring on an oscilloscope, it would be 120 times root 2, which I think is around 170. But 120 is the RMS value here. Okay. And this is the equipment, 100 ohm resistor. And so let's start the clicker. You're going to turn the equipment on. You want to run that equipment for 24 hours. How much energy is needed in kilowatt hours? Give that a shot. Just take a couple minutes and try to figure that out. So, right, kilowatts, that's a unit of power. You can calculate power from what you have here, right? You can calculate that power. You have voltage, you have resistance. You know how many hours, 24 hours. And then there's some conversion in there. All right, take another minute. And so a lot of these calculations are, can be dissected by the units. We can figure out power from the voltage and the resistance, convert that to kilowatts, multiply that by hours, which is, that's how your house power is measured. So if we wanted to know how much would we pay for operating this equipment for 24 hours, we'd get the amount in kilowatt hours, and then your energy delivered to your house is billed to you in cents per kilowatt hour, usually somewhere around 10 cents around here, and more expensive in other parts of the country. All right, so let's take a look at this. Okay, so power average is RMS voltage squared over R, 120 squared over 100, that's 144 kilowatts. Doesn't look right. Oh, no, that's right. That's right. Watts. So that's 0.144 kilowatts times 24 hours. And so 3.456 kilowatt hours. So if you ran this system for 24 hours plugged into your wall and you lived somewhere around here where power is 9 or 10 cents, let's say 10 cents per kilowatt hour, this would cost you 34 cents to operate for, uh, oh, wait, that would be 10 hours. No, that's right. 10 cents per kilowatt hour, 34 cents to operate this for 24 hours. Okay, so that's great. I made this up, but why does this matter? Well, you could imagine that you can convert the specifications for this battery into how much energy does it have stored? And does this battery have enough capacity in energy to power this system for 24 hours, right? You can also compare energy efficiency of approaches, right? You could, for a certain circuit, you could figure out how many kilowatt hours or joules or whatever unit a circuit consumes. You can look at different approaches. You can calculate, just like we did, cost of energy to run the system, maybe not for a day, maybe for a month, or maybe it's, we have to run it for a year. How much do we have to budget to run this for a year? So that's what it's good for. Okay. All right. So also applying Ohm's law, let's talk about a practical resistance and example, because we ran into this last year in lab, which is why you have a circuit board for your motor driver this year and you're not using the breadboard. Wires and breadboards are non-ideal conductors, which means they have non-zero resistance, right? They don't have infinite conductance. Wire resistance causes a voltage drop between the two wire ends. So depending upon where you measure voltages in a circuit, you might see different voltages because of the voltage drops across wires, and power dissipation occurs when current flows through a wire, right? And so the junctions, the connections of wires to components and boards, like poor solder joints or breadboard connections or splices or corroded terminals, they can also cause a voltage drop. Okay, so, and again, in lab last year when we ran this class, it was unexpected the amount of resistance that we encountered for the breadboard. So this is a real thing. If you're using currents that are more than a few milliamps, you could experience some problems. So here's an example. Measured wire resistance. You take your jumper wire from your lab kit. You're going to get these next week. And the one I used, I think you have 8-inch wires. This one was 5 3/4 inches right here. So here's a wire under test. And so I actually said, what, does this matter? Do I really care that these are thin wires and that we're using a couple amps for motors? Well, what you can do is you can use high current and Ohm's law rather than an ohm meter for better accuracy. So if you measure this wire with an ohm meters often are not very accurate in the kind of sub 1 ohm level. So what I did is I connected a 2 amp current source, just used a power supply, and measured this wire under test. And then I took a voltmeter and I measured the voltage at the ends of the wire. Okay. And here's what I saw with these voltmeters, right? I saw I'm putting 2 amps through this breadboard wire. 2 amps isn't that much, but the breadboard wires are thin. And I saw 128 millivolts, which that's not zero. That's not zero voltage, right? So here's the setup here. So I had 2 amps, measured 128 millivolts. That means the resistance is 0.06405 ohms, which is really small, right? That's your voltmeter. Many voltmeters would have a hard time measuring that and distinguishing that wire resistance from the resistance of the test leads. Okay, and typically wire resistance is given in ohms per 1,000 feet. Okay, so this many ohms, right? Right, how much would that be in ohms per 1,000 feet? It would be 133.6 ohms per 1,000 feet. Okay, and that's far from ideal, right? 133.6 ohms per thousand feet is not ideal. So we're going to see some practical examples of this, especially in higher current applications where even with thicker gauge wires, where if you're installing like, solar on your house, you're going off grid with solar panels, it really does make a difference. And the configuration that you set up can make a difference on power efficiency. Okay, so we'll get into this a little more next time, but I have hit the wall on time for right now. So don't forget, check out Canvas for the upcoming assignments. Homework 1 is due next Friday, 9/6. So take a look at that, and we'll cover more of this material on, let's see, Wednesday next week, because Monday's a holiday. Your first lab will be next Friday, also on the 6th of September. Check out the ITLL workshops. So they fill up quickly. If they do fill up and we have high demand, we might be able to get a special session. But if you want this, I would recommend, if you don't have any Arduino experience, check that out. If you don't have any soldering experience, just go sit down and you can solder on some practice components before you do it for score, on your project. It's not really for score, but you'd rather mess up on someone else's components than your own and have to desolder them. So check out those workshops, check out the review videos. If anything I'm talking about, you want some refresher on, and those are linked on Canvas. So I will start office hours right after we end this class. If you'd like to stop by and chat or have any questions, please do so. If you don't, I'll see you next time, which will be next Wednesday. Have a great night.